So let us start. And this is lecture 13. And as always, let's start with recalling what we did last time. So one of the main point was that we can map if we have a vector space and the dimension of this vector space is n, then we can map in a one-to-one fashion this vector space to the vector space of n component columns. And how we do it is by mapping basis to basis. And everything else just follows from there. So if you have a basis for this vector space V, and then you can map it to the standard basis of Rn by simply taking each basis element and mapping it to corresponding standard basis. So what it will do is that if you have any vector over here in V, this is the most general vector in V, because you can expand any vector in terms of the basis elements with choosing some appropriate coefficients. So this is mapped simply to this column. The coefficients in a basis specify the vector completely. So I can collect those coefficients and arrange them in a column. So I have got a map from V to Rn. But we should note that this mapping is not unique. It's not unique because we can choose different bases in V. So in different bases, you will have different numbers. So the same vector V in another basis will have different number. So if these dashed V1, VI's are also form a basis, if I'll write this vector as a linear combination of this new basis elements, then I'll have different coefficients. And if I map this basis to the standard basis of Rn, then I'm collecting these numbers. So you have many different choices available how to map this vector space to Rn, and it's essentially related to which basis you map to the standard basis of Rn. Then we had also that in Rn, when we define a vector as a column of numbers, like this. Let's collect these numbers. Then these numbers, these are actually also coefficients in the standard basis. Coefficients, coordinates, components all mean same thing, because this same vector C1, C2, Cn, I can write it as a linear combination of these guys, the standard basis elements. So these coefficients, these components, the way you had defined this vector, are actually also the coefficients in the expansion in terms of this basis, standard basis. But we can also choose another basis. Let's say ui, and the same vector will have an expansion in these new bases as well. So I will have v as a linear combination of this basis vectors, but I'll have different coefficients for them. We saw some examples of this changing the basis last time. And so what I have over here is n, because in the basis, remember, it's an n-dimensional, it's Rn, so the basis is n elements. So I'm specifying, I can specify this vector v by listing these n numbers, d1, d2, up to dn in this basis. That completely specifies this vector. So I can collect them as well in a column. But this column, now I'm thinking of it, this is a representation, that's what I call it. Representation of V, that same vector, which I had given by listing C1, C2, C3, now it's represented by different numbers. The representation of V in UI basis. And if I collect these guys, this is representation of V in standard basis. So if I want, although these are representations, I can, but they are still look like vectors and a column of n numbers. So I will still write them with this vector notation, where this is a column and there's a slight chance of confusion. So I have a vector, it is also defined in a way, it's defined by giving n numbers, but on the other hand, I can have its representation, which is also given in terms of n numbers. But I'll interchangeably write this kind of symbol for representation and the vector itself, and it will be clear from the context what we are talking about. One thing you can note that the representation, as what we had just said, the representation of your vector in the standard basis is same as the vector. So the representation of V is in standard basis matches with the originally defined vector. It so happened that we had defined the vector by giving a list of n numbers. And that list matches with the representation in the standard basis, but the representation in other bases will have a different list. So this thing becomes more clear if we think geometrically. So I have this x and y axis. So we know that if I have a vector v in Rn, it defines a point in geometrical space of having x and axis. It defines a point in a geometrical space. So if I'm, for example, in R2, it defines a point in plane. So these two numbers, v1, v2, they give me the coordinates of a point. Then I can draw a vector going to that coordinate. But once I have drawn it, I can forget about these numbers. This vector is just a directed line which exists in its own right, and I know how to add these directed lines. So once I have drawn these vectors, I can forget about these numbers. These numbers came in only because I chose a coordinate system x and y. I chose these coordinate lines, and with respect to these, I could give some numbers to draw this line. So they were corresponding to these I and j. But someone else, this was just a plane, and this directed line, this vector was living here, and you drew these x and y axis to give these numbers. Someone else might be using some other lines or some other basis vectors. Let's say these ones. And this is u1, this is u2. You can resolve this vector in terms of these bases as well. You can write this vector, this red vector, in terms of these purple u1 and u2 as well. And for that guy who started with this, they don't know that you drew I and j to start with. For them, these u1 and u2 are good enough. So what they can think of is that for them, u1 and u2 is the starting basis. So they will call that as the standard basis. So they will write naturally that u1 is something like that, and so on. So for them, the representation in the U basis is the starting definition of the vector because it gives you the coordinates in their standard basis. So in this sense, each representation is on an equal footing. With one standard basis in mind, so you have one standard basis in mind geometrically, we have one representation matching with the column vector definition. You initiate the vector, you define the vector as a column with one basis in mind. So that becomes your standard basis. And then you can change basis if you like. So how to change basis? Starting from 1, we saw this last time, that for representation columns, which are these C and Ds, C is in standard basis and D is in any other basis. We saw that we can go from this D to C by applying this matrix U, where U is simply this matrix. Matrix constructed out of the columns of U in the standard basis. Columns of UI in standard basis. And note that if I write this any of this one of this basis vector, if I expand it in the standard basis, I will get some numbers. I will have some expansion. Then these expansions I can collect. I can list all these expansion and give it a form of a matrix. Because I know how the matrix multiplication works. So I see that if I write something like that, this first row of this matrix, when it multiplies the first column over here, it constructs for me this linear combination. So I can collect all these linear combinations and write them in matrix form. So on. But if you look at one of this row, the first row, what are these? The first row are the components of U1 in standard basis. Or it's just the column of U1 change into the row. And U2, the second row, is similarly column of U2 change into row. So that means this vector, this matrix A is actually this U which you constructed above, which were the columns of U1 change into rows. So this is just U transpose. Therefore, you can change, you can write the new basis elements as a linear combination of the standard basis using this matrix. Now this was how to, if I look at this equation, let's call it 1. This is telling you that how to go from the representation column in the new basis to the representation column in the standard basis, or going back to the original vector. But this, what is more interesting is that if you are given the original vector, that means you are given the representation in the standard basis, and you want to get the representation column in some new basis. That would be the more interesting thing to do, because you suppose that you are given a vector and you want to change its basis. So how will that work? So what you want, given the C, find D. Now, if I look at this matrix U, this is just this. And since I know which basis I'm going into. I know what this U1, U2, U3, UN are, so I know this matrix. Now, using this matrix, I consider this equation. This matrix acting on an n unknown column or some different column. So this, when I open it up, it is simply this one. I know that this is how I multiply a matrix with a column. This is one of the ways. X1, X2, Xn. This is how you multiply it. Take the linear combinations of the columns. And this has to be equal to the zero column. Now, I know that Ui are linearly independent. That means this would be zero if and only if all xi are zero. So the only solution, this means that the only solution of this equation is that x is equal to 0. So it has a unique solution. But this equation has a unique solution. We did this theorem some time ago, and we hammered it many, many times, that this equation has a unique solution if and only if U inverse exists. U is invertible. So that would mean, starting from this equation, which we just had derived, I can multiply both sides by U inverse and get D is equal to U inverse C. So so your strategy would be that you are given the new basis, arrange them in a matrix U, find its inverse, and apply that inverse onto your original vector, and that should give you the representation of that vector in the new basis, or its components, its expansion coefficients in the new basis. So let's do an example of this. So suppose we are in R2. This is my standard basis, and I change it to this basis. Remember, if I have to collect these coefficients in the column, I have to give an ordering, that which one I call the first vector in the basis, which is second, and so on. So geometrically, what you are doing is, this is your standard basis, Ij. You have replaced it with, the first is, this guy is just j, and this guy is minus I. You have placed it with j and minus I in this order. So in a sense, you have rotated your original vectors rigidly, and which brought this j to minus I and I to j. In any case, this is your new basis. So your matrix U is just, you arrange these vectors in your new basis, 0, 1, minus 1, 0. Now all you have to do is find its inverse, which is fairly easy to find. So I interchange the rows. This goes to 1, 0, 0, 1, 0, minus 1, 1, 0. And I have to make an identity on the left hand side. So I just multiply the last row, second row by minus 1. So this becomes 0, 1, minus 1, 0. So that means this guy is U inverse. So U inverse is 0, 1, minus 1, 0. So therefore, if I am given AB as original vector, and if I want to find representation in new basis, that would be some new number CD, and you can find them by multiplying with this inverse matrix, the original vector. So it would be B minus A. In other words, this AB has an expansion B. This was our first basis vector minus A second basis vector. We had done this by directly last time, but this time we are doing it in a systematic way. We had done another example last time. So let's do that also in this systematic way. We had this new basis. And we saw that how would any vector be expanded in terms of this. So if I do it this way, I construct this U, which is first vector and the second vector. And now I have to find the U inverse. So for that, I start from here. I eliminate this one. So I add minus time first row to the second. I get this. And then I want a 1 here, so I can multiply the second row by minus half. So I get a 1 here and a half here, a minus half here. Now I just have to make this 0. Make this entry 0. So I just multiply the second row with minus 1 and add above. So I get my computer turned off for some reason for a second. Can someone tell me, am I still audible on the other side? Did I get disconnected or not? Can someone reply? Can you hear me? Okay, thank you. So I got a 0 here and minus half plus 1 gives me a half, and minus times minus half above gives me a half. So I get U inverse equal to half, 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 minus half. And then my any vector, original vector, will go to this CD equal to half, half, and this just gives me half. Well, let's write it directly. A plus B and A minus B. And that's what we had found last time. These are the coefficients in the expansion in the new basis. And if you collect them in a column, you just call it the representation in the new basis. Let me do another interesting example. This is a new basis, which is just rotation of standard basis. So what are we doing? We have this x and y, I and j. Now I rotate the axis or rotate these vectors. So when I rotate by an angle, let's say theta, I'm rotating the whole plane. So x and y, they rotate together. So if I have generated an angle theta here, there's the same angle theta of this. So this is my new x dash and this is y dash. So I will have a new basis vector along this x dash direction I dash and a basis vector along this new y dash direction j dash. And now I can do simple trigonometry. If this is I dash and it's a unit vector, I want to write it as a sum of the original basis, which would be this I plus some portion of j, some portion of I, and some portion of j. So how much I is there? If hypotenuse is 1, then the base is just cosine theta. So my this rotated I dash, new I dash, this guy is just sum of I and j with appropriate coefficient. And how much I? Just the length of this base here. So the base is cosine theta. And how much length is here? Hypotenuse, remember hypotenuse is 1. I'm creating a unit vector. So hypotenuse is 1, then this perpendicular is just sine theta. So I need sine theta length of j. So I add this cosine theta I, this plus sine theta j, and I will have created this new unit vector in the direction of rotated x-axis. Now, what would be j dash? Again, it has to go, I have to add some part of j like this and some part of I dash, actually minus I dash is directing in the opposite direction. So how much is this part? This angle is theta. So this part is base. So this is cosine theta j. And I also have to add this portion is perpendicular in this triangle. So that's sine theta. So I have to add minus sine theta I because it's directed in the direction of minus I. So that means these are my new basis vectors, and their u is simply, I collect these. Cosine theta, this is the first vector, and this is the second vector. Because this new I dash, I can write it as this, and j dash is so if you want, I know that U transpose is this guy, and I knew that this matrix should work out. And that's exactly what it is. If you look at these guys, I can write it in matrix form. And this matrix is exactly U transpose. Now I want to write any vector which was given to me in the original ij in terms of these rotated I dash j dash, in terms of the rotated axis. For that, I need to have the U inverse. You can calculate it, but I'm just giving you the answer. It's very easy. It's actually the U inverse in this case is just U transpose. We can just check. So U inverse is cosine theta, sine theta, this was U had a minus here. Yeah, this is not U inverse. This was U. Wait. Minus sine theta, sine cos theta. Yeah, that was U, and this is U inverse. So U had a minus here, and U inverse has a minus here. So I can very easily check. When I multiply them, over here I get cos square theta plus sine square theta. And remember, theta is arbitrary. It's for any rotation with any angle theta. Over here I get cosine theta, sine theta minus sine theta, cosine theta. So this is 0. And over here, sine theta, cosine theta minus cosine theta, sine theta, 0. And at the last thing, I get sine square theta plus cosine square theta. But these are 1. We know this trigonometric identity. So this is just 1, 0, 0, 1. So that matrix indeed is U inverse. That means if you are given the coordinates A, B in 2 dimension in the standard basis, you can find the rotated coordinates by multiplying with the inverse. So it would be just cosine theta A plus sine theta B and minus sine theta A plus cosine theta B. So you can check if I rotate by 90 degree for theta is equal to 90, what would be this matrix? This U inverse. U inverse at 90 degree is 0, 1, minus 1, 0. So if I take this vector, I vector, it should, after 90 degree rotation, it should become the J. And 0, 0, minus 1, 0, theta. Well, we did it wrong. Sorry. At 90 degree, sine theta. This is fine. 0, 0. I get a 0, and I get a minus 1 here. So this is rotation in this direction. Let's take another example. Oh, well, because I was rotating the vector. Let's take this example. You have standard basis. We have polynomials. Now we are in the space of polynomials of degree 2. And this is a standard basis. So if I have this polynomial can be represented. I just have to collect the coefficients in the standard basis. And I'm looking at the coefficients right over here. So this is how it's mapped to Rn. Now, if you are told that there's a new basis, which is this one, these polynomials. So these three vectors, let's call them U1, U2, U3, are a new basis. How do they look like as columns? So this is just 1 minus 1 in the standard basis. U2 is 1, 1, minus 1. And U3 is there's no x square, so you have a 0 there, 1, minus 3. So that means this U is 1, minus 1, 1. Collect the first vector, and then collect the second vector, and then collect the third. This is your U. And to go from the standard basis to this basis, the components, to transform the components, you need the U inverse. I'm not gonna waste time in calculating that. I had calculated it at home. And you get it, you get this. This is the inverse of U. So that means that if I want to I had the representation of that polynomial in the standard basis. I can get the representation in this new basis by multiplying with U inverse. So what do I get? Let me write it directly. 3 by 2 minus 3 by 2 minus 5 by 4. And then you have 3 by 2 plus 3 by 2 plus 5 by 4, 0, and then minus 1, and then minus 5 by 2. So this gives you minus 5 by 4, and over here you have 6 plus 6, 12, 12 plus 5, 17. 17 by 4, and over here you have minus 7 by 2. So that's the representation. And that means that this polynomial can be written, you have kind of done this using this matrix techniques. You have found an expansion. This must be equal to x square minus x plus 1, the first vector coming here, and the second was x square plus x minus 1, and the third was x minus 3. So these two sides are equal. You have kind of, if you want to convert one polynomial as an expansion in terms of other 3 polynomials, you can use this technique. Now you can generalize this change of basis. So far we have been doing it in how to go from the standard basis to a new basis. You can very easily generalize to a general basis transformation. So you are given 2 bases, and neither of them is standard. So I know that this standard basis, this basis would be, if I make this U by writing these, and I make a V similar matrix by writing the V basis vectors, then we have seen that this UIs would be just this matrix product. Take the transpose of U and make the matrix product. And when I pick an I from that matrix product, I'm picking the ith row. Similarly, I will have Vi with V transpose Ij, Aj. So if you have any vector, it will have some expansion in the UI basis and also some expansion in Vi basis with different coefficients. We want to go from one set of coefficients to the other. The set of coefficients is the representation. So I just replace these UIs and VI from here, from A and B. From A and B, I get over here. So I get AI U transpose IJ EJ equal to BI U transpose. By the way, I forgot to write because I'm so used to of not writing these, but for you, I think it's important that it's a matrix product, so you have a sum over J and you have a sum over I. And I hope I didn't miss this sum anywhere else. For I'm personally used to, because when you are comfortable with linear algebra, people, whenever they see a repeated index, they just assume that there's a sum, so they don't write it. So that's why I just had this little trouble. So wherever you see repeated indices, just put a sum. So I have a sum, and since I place these guys, let me write. There's about a sum over J. Sum over I, sum over J, EJ. Not EJ. Yeah, EJ. Now I can change the order of summation and collect these. Bring it to the other side. One was U, one was V. This was V. Bring it to the other side, and you have this equal to 0 because I brought it to the other side. And there's a sum over I. Now, but since EJ, they are a basis. This is the standard basis. So this can be 0, that means they are linearly independent. So this can be 0 only if all these coefficients. So what you are doing, you are taking these EJs, some linearly independent vectors, multiplying them with these numbers and summing. This J is summing over it, and to get a 0. But we know that for linearly independent vectors, that can only happen if each coefficient is 0. So in this case, the coefficient turns out to be these guys. And they are all 0. So I can open the sum and take 1 to the other side. I can use the transpose property and write it as Vji. When I replace the transpose, sorry, this is U. Rows and columns are interchanged. I and J are interchanged with J and I. And I can write U first, A second. These are just numbers. Doesn't matter which order you write. Just for clarity, I'm writing A on this side. So over here also, I do this. But now I am summing over the columns of U with the rows of A. So this is a matrix product. So this is all it's saying, that you're picking the picking the jth row from this matrix product. So all the rows are equal, and this equation is same as this. But since u's are invertible, we just argued that u have to be invertible. Similarly, if you make them out of those some linearly independent vectors, that's what we had done. Similarly, v are invertible. So I can take one to the other side, multiply with u inverse on both sides, and this gives me 1 in terms of the other. So how you do it? You want to go from B to A, write the matrix of the matrix of coefficients of vectors in V basis. Then write the inverse of the matrix where you want to go. In U basis. And this is representation in V basis. And this is the representation in U basis. So you can very easily do it. Now, I think we have done enough of this change of basis, done some example. Let me move on to a new concept, not totally new. So first of all, let's recall that we had row vectors as well. So then I have row vector space n tilde. I'm just going to put tilde. This has vectors of kind v1, v2. Oh, sorry, there's no. Let's put it like this. C1, C2 numbers, C3 up to Cn. So you collect n numbers, but instead of writing them in a column, you just write them in a row. So these guys also form a vector space by, if you add them term by component by component, we know that very easily, clearly. Now, in this, you can consider this standard basis. Similarly, as before, only at the ith place, you leave a 1 and the rest are 0. Then you have a very natural map. Remember that I had said in the start of the course, I'll write the column vectors with an arrow and the row vectors with a bar. So let's suppose that there's just a bar. So these are standard basis row vectors. And I can map them naturally to the column vector. Just map it to the ith standard column vector. And what is it? It's just the transpose. So if you have this guy, you take the transpose, you get this guy, changing the column into row. So there is not much difference between this row space and the column space, vector space. You take the column vector and take the transpose, it becomes a row and it's a space as well. But what's a row space of a matrix? So for any matrix A, well, actually, it doesn't have to be a square matrix. M by n size matrix, how many rows are there? There are m rows, each of length n. So you can think of this A as composed of m row vectors, where each one of them is an n-dimensional row vector. This is all repetition of what we did a long time ago. Now, all of these row vectors, they belong to this space n, because they are n-dimensional. Sorry, I had written n over there. N-dimensional row vector space. But I know that if I make a span of any number of vectors, that gives me a subspace of Rn. So a span of row vectors of A will give me a subspace of Rn. So this subspace, whatever I get, is called the row space of the matrix. This is the row space. Similarly, this matrix AMN also can be thought of as having n columns, each having m components. So clearly I can write it as n of them, each ui is m dimensional. So dimensions are different. So I take all columns in A and span them. So we know that this has to form a subspace. This will form a subspace of the space where they live. So where do they live? They live in the m-dimensional column vectors, Rm. This would be called the column space of this matrix. So given a matrix, a fixed matrix, you can consider its row space and its column space. And how do you construct the row space? You take all the row vectors and make all linear combination. What is the span? It's the all linear combination. So all vectors of this form this would be the span. Now, m could be smaller than n, m could be bigger than n. So suppose if m is less than n, these vectors v are a subspace of R tilde n. But then you will have, if m is less than n, then you will have only m of these. So even if they are linearly independent, they will not generate the whole Rn. It will be a subspace. But if m is equal to n or greater than n, then you have a chance that you can even generate the whole space R tilde n. Let's consider some examples. So let's consider this matrix. So the row vectors live in three-dimensional space. And what is the span? Which is the row space. These are all vectors of this form. You take the row vectors and make arbitrary linear combinations. So these are vectors of this form. So we know that this is a two-dimensional subspace of R tilde 3. R tilde 3 is three-dimensional, but you have your row space is two-dimensional. What is the column space for this? So how many columns you have? You have 1, 0, 0, 1, and 0, 0. And they live in R2. They belong to R2. But the span is vectors of this form. Which is just alpha beta, and alpha beta are arbitrary R. But this is just equal to the complete R2. That's what R2 has. All alpha beta columns with alpha beta arbitrary. So the column space is equal to R2, the full space. So the subspace of row space or column space could be equal to the whole space or a proper subset of it. Now there's a very important, so this thing, there's a definition, rank of a matrix. It's called written rank of A. This is just the dimension of row space of A. So if you have m by n matrix, it has m rows and each is n-dimensional. Now, if m is equal to n, then you have m rows, each having n dimensions. Each is an n component row. Now, if it so happens that all of these m rows are linearly independent, then we know that n of them will form a basis for R tilde n. So in that case, if they are linearly independent, rank of A would be equal to m equal to n. But if they are not linearly independent, then they cannot span the whole space. So they will span a subspace. Then rank of A would be less than n if they're not linearly independent. On the other hand, if m is bigger than n, again, they are n-dimensional, so at most, they are n components, at most they can span an n-dimensional space. Even though we have more than m, but we know that if we have more than m, they cannot be more than n, then they cannot be linearly independent. So rank of A would still be equal to or less than n, the second number in am by n. And if m is less than n, then rank of A is anyway has to be less than n. If m are all linearly independent, it will be equal to m. If they are not, it will be less than m even. So it always is less than the number of equal or less than the number of columns. So there's a very interesting theorem to find the rank. It says that two row equivalent matrices have the same row space. So how is the proof? So if A is equivalent to B, so that means you can make row operations on A and go to B. That means, or row operation on B and go to A, if A is equivalent to B. Rows of A are linear combinations of rows of B. That's what it means by definition. But that means that the rows of A, these vectors, row vectors, are, because they are linear combinations of rows of B, are in the space, in the row space of B, because they are in the span of B, row space B. But that means if I span using these vector, because these vectors live in the span of B, so span of rows of A will at most give me a subset of span of rows of B. Because rows of A, these vectors already live in the span of B. So when I span using them, I will not create anything new. I will get some subset of span of B. But I can reverse the logic, because if A is equivalent to B, if I can go from B to A using row operations, I can come back. B can also be reached by using row operations on A. So you can reverse the role of A and B in above lines to come to conclusion that span of rows of B is contained in span of rows of A. So that's only possible if they are same. So that means, but span is just the row space. So this has a very interesting consequence. Row operations do not change the rank of a matrix. Well, actually, more general, row operations do not change the row space of a matrix. Because by row operations, you get an equivalent matrix and they have same row spaces. If they have same row spaces, the dimensions are same as well. So, for example, if I consider this matrix, and I want to find its rank. So I have to find the dimension of its span. What I can do, I can go to its echelon form, and its echelon form turns out to be this. Now I can see that a span, this is zero vector, so this does not count in the span. This vanishes, so the span is two-dimensional. That implies that the rank of the original matrix itself is 2. So that means also that the three row vectors in A are not all linearly independent. So I'll stop here. Is there a question?